Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Step 1 is assignment rules. For each double bond, identify the two substituents on each carbon of the double bond. Rank by CIP priority. Higher atomic number is equal to higher priority. If the two higher priority groups are on opposite sides E, same side Z. If both substituents on either carbon are identical N, no EZ isomerism possible. Part A. Double bond 1, exocyclic is equal to CMe2 on the isopropanol side chain. Both substituents on the terminal carbon are methyl groups, identical, so no EZ isomerism. N. Double bond 2, endocyclic double bond in the cyclohexene ring with a methyl substituent. The ring carbon has two different ring chain substituents. Ranking gives Z configuration. The higher priority groups are on the same side of the double bond. Z. Double bond 3, internal double bond in the large terpenoid, trisubstituted assign CIP priorities to substituents on each alkene carbon. The higher priority groups end up on opposite sides E. Double bond 4, endocyclic double bond in the bicyclic ring system. The ring constrains the geometry. Analysis of the substituent priorities gives ZZ. Double bond 5, first double bond of the polyisoprenoid chain of ubiquinone, adjacent to the aromatic ring. The two carbons of this double bond bear different substituents. Priorities give ZZ. Double bond 6, next internal double bond in the chain. Priorities give opposite arrangement. E. Double bond 7, terminal is equal to CMe2. Both groups on the terminal carbon are methyl, identical, so no EZ isomerism. N. Part A answer 1-N, 2-Z, 3-E, 4-Z, 5-Z, 6-E, 7N. Part B. A. Bonchraic acid double bonds. Double bond 1, near lower ChO and the carbon bearing ChO and the carbon bearing the chain substituents. CIP ranking places higher priority groups on the same side Z. Double bond 2, next alkene, near upper ChO. Higher priority groups on opposite sides E. Double bond 3, internal, shown with filled wedge context indicating configuration. Higher priority groups on opposite sides E. Double bond 4, further internal. Higher priority groups on same side Z. Weight reassessing. The arrow and structure show this double bond in the middle section. CIP analysis gives Z. Double bond 5, near OCH3. Bearing carbon. The OCH3 group is on a sp3 carbon adjacent to this double bond. Analysis gives ZZ. Double bond 6, near right ChO and higher priority groups on opposite sides E. Part B. A. Answer 1-Z, 2-E, 3-E, 4-Z, 5-Z, 6E. Part B. B. Total stereoisomers. Bonchraic acid has 6 EZ double bonds, each contributing a factor of 2, and the OCH3 bearing carbon is a stereocenter, one chiral center, contributing factor of 2, but one of the double bonds, if endocyclic or constrained, may be fixed. Actually, 6 double bonds plus 1 chiral center, the OCH3 carbon, plus possible additional stereocenters is equal to total stereocenters count is equal to 9 independent stereoelements, giving to 9 is equal to 512 total stereoisomers. Part B. C. Sites of unsaturation, degrees of unsaturation. Bonchraic acid molecular formula C18H30O5. Do U is equal to 2 times 18 plus 230, 2 is equal to 36 plus 230, 2 is equal to 8 halves is equal to. Recalculating with correct formula for bonchraic acid C18H30O5, do U is equal to 218 plus 2-30, 2 is equal to 38 to 30, 2 is equal to 8 divided by 2 equals 4. That seems low. The actual molecular formula of boncraic acid is C28H38O6. Do U is equal to 2 times 28 plus 2 dash 38. 2 is equal to 58 to 38. 2 is equal to 20 divided by 2 equals 10. So there are 10 sites of unsaturation. 6C is equal to C double bonds plus 2C is equal to O of 2 groups times 2 COHs plus, totaling 10. Therefore, the correct answer is A, 1N, 2Z, 3E, 4Z, 5Z, 6E, 7N vertical bar B, A, 1Z, 2E, 3E, 4Z, 5Z, 6E, B, 2, 9, C, 10. The correct answer is shown on screen.